4.5 billion years ago, in the violent chaos of a young solar system, cosmic debris collided in a dance of fire and ice. From this celestial fury emerged something extraordinary, a pale blue dot that would defy all odds. This is Earth. But the planet you think you know is not the planet that was. Our world has died and been reborn countless times, frozen solid for millions of years in ice ages so severe they turned Earth into a giant snowball, bombarded by asteroids the size of mountains, suffocated by toxic atmospheres. Yet somehow, impossibly, life not only survived, it thrived. But where did the very water in your body come from? The answer lies not on Earth, but in the depths of space itself, a cosmic delivery system that transformed a barren rock into an oasis of life. Every 26 million years, our planet faces Judgment Day. Massive objects hurtle through space on collision courses with Earth. The dinosaurs learned this lesson 66 million years ago. The question isn't if the next one will come, it's when. Throughout this epic story of survival against impossible odds, one question haunts us: are we alone? In a universe containing more stars than grains of sand on every beach on Earth, the mathematics suggest we cannot be the only experiment in consciousness. Yet, the silence is deafening. Tonight, we'll journey through 4 billion years of Earth's most incredible secrets, from the mysterious origins of our life-giving oceans to the cosmic forces that have shaped our destiny, from ice ages that nearly erased all life to the asteroid impacts that rewrote evolution itself. This is the story of Earth, a story of death, rebirth, and the endless search for our place in an infinite cosmos.
Our planet wasn't always the blue oasis we know today. Around 4.5 billion years ago, Earth formed from a swirling disk of dust and gas orbiting the young sun. In its infancy, our world was a molten hellscape, bombarded by asteroids and comets in a violent era called the Late Heavy Bombardment. With surface temperatures hot enough to vaporize rock, any water present would have instantly turned to steam and escaped into space. So how did Earth go from a scorching wasteland to a planet 71% covered in water?
For years, astronomers believed Earth's water arrived after the planet had cooled, delivered by icy comets from the outer solar system. These frozen wanderers, often called dirty snowballs, seemed like perfect candidates, packed with ice that could melt upon impact, filling young Earth's basins with life-giving water. But when scientists began analyzing the chemical fingerprints of comet water, they hit a snag. The ratio of deuterium, a heavy form of hydrogen, in comet ice didn't match the water in Earth's oceans. If comets were the main source, our oceans should have a different chemical signature. This discovery forced researchers to look elsewhere for Earth's water, and they found a surprising alternative: asteroids. Not all asteroids are dry, rocky bodies. A special class called carbonaceous chondrites contains surprising amounts of water locked within their minerals. Even more compelling, the deuterium ratio in these asteroids matches Earth's oceans almost perfectly. This revelation turned planetary science on its head, suggesting that while comets may have contributed some water, the bulk likely came from asteroids that bombarded Earth during its fiery youth. The Late Heavy Bombardment, a period of intense asteroid impacts between 4.1 and 3.8 billion years ago may have been the critical delivery event that filled Earth's early basins with water. But the story doesn't end there. Recent research suggests Earth might have been wetter from the start than we ever imagined. Some scientists now believe water was present in Earth's building blocks from the very beginning, trapped within the minerals that formed our planet. As Earth's interior cooled and solidified, this ancient water was gradually released through volcanic outgassing, creating the first thick, steamy atmosphere. Over millions of years, as temperatures dropped further, this vapor condensed into rain, torrential downpours that may have lasted for millennia, slowly filling the low-lying basins that would become our first oceans. This theory paints a picture of a planet that never truly lacked water, but instead cycled it between its interior and surface over billions of years. The mystery of Earth's water extends far beyond our planet. The same processes that delivered water to Earth may have played out across the solar system, leaving traces on worlds we once thought were bone dry. From the icy plumes of Saturn's moon Enceladus to the vast subsurface oceans of Jupiter's Europa, water appears to be far more common in our cosmic neighborhood than we ever imagined. These distant worlds, frozen in time, may hold clues not just to how Earth got its water, but to how life itself began in the primordial soup of our young planet. As we continue to explore these alien oceans, we edge closer to answering one of humanity's oldest questions. Are we alone in the universe, or is water, the elixir of life, as common as the stars themselves? The journey of water to Earth is intertwined with the chaotic early history of our solar system. As the young sun blazed to life, it created a swirling protoplanetary disk of gas and dust where planets were beginning to take shape. In these turbulent conditions, water molecules could only survive in the colder outer regions of the disk, beyond what scientists call the frost line, a boundary where temperatures were low enough for water to exist as ice. This explains why the inner planets, like Mercury, Venus, and Mars, formed relatively dry, while the outer planets and their moons became reservoirs of frozen water. Earth, sitting in a precarious middle ground, somehow managed to acquire and retain enough water to become the life-bearing world we know today. The process of water delivery to Earth was likely a complex interplay of different mechanisms. While asteroid impacts provided much of our water, recent studies suggest another fascinating possibility: that water vapor could have been directly absorbed by Earth's growing mantle from the surrounding nebula. This means some of Earth's water might have been present during the planet's formation, trapped within the very rocks that built our world. Additionally, the solar wind, the constant stream of charged particles from the sun, may have contributed by interacting with oxygen-rich minerals on asteroid surfaces, creating water molecules that later hitched a ride to Earth on these space rocks. The timing of Earth's water arrival is equally crucial to understanding our planet's evolution. Evidence from ancient zircon crystals in Western Australia, some dating back 4.4 billion years, suggests liquid water existed on Earth's surface remarkably early in its history. This challenges previous assumptions about how quickly Earth cooled and developed stable bodies of water. These microscopic time capsules tell us that oceans may have formed just a few 100 million years after Earth itself, creating the stage where life's drama would eventually unfold. The presence of water so early implies that the delivery process was not just a single event, but rather a continuous rain of water-bearing objects over hundreds of millions of years. Mars tells a cautionary tale in this cosmic water story. The red planet shows clear evidence of ancient river valleys and lake beds, proving it once had liquid water on its surface. But unlike Earth, Mars was too small to maintain its water over geological timescales. Its weaker gravity couldn't hold on to an atmosphere thick enough to keep water liquid. And without plate tectonics to recycle water and minerals, Mars gradually became the arid world we see today. This stark contrast highlights how Earth's size, magnetic field, and geological activity made all the difference in preserving its precious water resources. Looking beyond our solar system, the discovery of water vapor in protoplanetary disks around other stars suggests that Earth's watery history might be common across the galaxy. The Kepler Space Telescope has revealed numerous exoplanets in the habitable zones of their stars, where liquid water could theoretically exist. Some of these distant worlds may have undergone similar processes of water delivery and retention, raising tantalizing possibilities about the prevalence of life in the universe. As we continue to study how water came to Earth, we're not just uncovering our own origins, we're developing the tools to understand how common water-rich, potentially life-bearing planets might be throughout the cosmos. The story of Earth's water is still being written. Each new discovery, from analyses of asteroid samples returned by spacecraft to observations of distant planetary systems, adds another piece to this cosmic puzzle. What began as a mystery about our own planet's past has blossomed into a fundamental question about the nature of planetary formation everywhere. As we stand on the shores of our oceans, looking up at the stars, we're beginning to understand that the water that makes our world unique is actually part of a vast, interconnected cosmic cycle, one that may have given rise to life not just here, but perhaps on countless worlds throughout the universe. The presence of water on Earth set the stage for something even more remarkable: the emergence of life. The same water molecules that arrived via asteroids and comets became the medium in which the first organic compounds assembled, interacted, and eventually formed self-replicating molecules. Recent experiments have shown that the conditions around hydrothermal vents in Earth's early oceans could have facilitated the formation of amino acids and other building blocks of life. These deep-sea environments, protected from the harsh surface conditions of the young Earth, may have served as natural laboratories where chemistry gradually crossed the threshold into biology. The water that came from space didn't just fill our oceans, it became the fundamental matrix in which life first stirred. The water cycle we know today, evaporation, condensation, precipitation, is just the surface layer of a much deeper planetary process. Earth's plate tectonics continuously recycle water between the surface and the mantle, with subducting oceanic plates carrying water deep underground where it's stored in minerals. Volcanic activity then returns some of this water to the atmosphere, completing a cycle that has operated for billions of years. This geological water cycle helps regulate Earth's climate and may explain why our planet has maintained liquid water for so long, unlike our neighboring Venus, where a runaway greenhouse effect turned all water into atmospheric vapor. The interplay between Earth's water and its geology created the stable conditions necessary for life to not only emerge, but to thrive and diversify over eons. Modern technology is allowing us to trace Earth's water story with unprecedented precision. By analyzing the isotopic composition of water in ancient rocks, in deep mantle samples, and in cometary ices, scientists are building a detailed timeline of when and how water arrived on our planet. Space missions like Japan's Hayabusa 2 and NASA's OSIRIS-REx, which returned samples from asteroids Ryugu and Bennu, are revealing that these space rocks contain not just water, but also organic molecules. These findings strengthened the connection between water delivery and the origin of life, suggesting that the ingredients for biology might be common throughout the solar system. The more we learn, the more it appears that Earth's water story is part of a grand cosmic narrative of molecular exchange between stars, planets, and the space between them. As we look to the future, understanding Earth's water origins becomes crucial for our survival as a species. The same processes that brought water to Earth, asteroid and comet impacts, pose existential threats today. By studying how water was delivered, we gain insights into planetary defense strategies against potential impactors. Moreover, as we search for ways to sustain human civilization, knowledge of Earth's deep water cycles informs our understanding of freshwater resources and climate regulation. The story of Earth's water, spanning billions of years from interstellar space to the glass in your hand, reminds us that we are part of an ongoing cosmic process, one that began with the formation of our solar system and continues to shape our planet's future. Ultimately, the water that fills our oceans, falls as rain, and flows in our veins is more than just a chemical compound. It's a cosmic traveler, a geological sculptor, and the essential ingredient for life as we know it. Every drop contains within it the history of our solar system, from the cold molecular clouds where stars are born to the violent collisions that shaped our young planet. As we continue to explore our solar system and discover water in unexpected places, beneath the icy shells of moons, in the shadows of lunar craters, and in the atmospheres of distant exoplanets, we come to appreciate that Earth's water is both ordinary and extraordinary. Ordinary in its ubiquity throughout the cosmos, yet extraordinary in how it transformed a rocky planet into a living world. The next chapters of this story will be written by future explorers who may find evidence of life elsewhere in our solar system, proving that the journey of water is indeed the journey of life itself. The story of Earth's water continues to unfold as we push the boundaries of exploration and scientific understanding. Recent discoveries have revealed that water exists in places we never imagined, trapped in the crystalline structure of minerals deep within Earth's mantle, suspended as vapor in the atmospheres of distant gas giants, and even embedded in the scorching surface rocks of Mercury. This ubiquity suggests that water is far more resilient and widespread in our solar system than we previously believed. The James Webb Space Telescope has detected water vapor in protoplanetary disks light years away, showing us that the same processes that brought water to Earth are likely occurring right now around countless other stars. Each new finding adds another layer to our understanding of how this simple molecule became the foundation for life on our planet. The chemistry of Earth's water holds clues to its extraordinary journey. When scientists examined the isotopic ratios of hydrogen and oxygen in different water samples, they can trace the water's history like detectives solving a cosmic mystery. The water in your body contains hydrogen atoms that have existed since the beginning of the universe, oxygen atoms forged in ancient stars, and a molecular structure shaped by billions of years of geological and biological activity. Some researchers have even found evidence that a small percentage of Earth's water may be older than the Sun itself, preserved from the interstellar medium that existed before our solar system formed. This means when you drink a glass of water, you're consuming molecules that have traveled across space and time, surviving supernovae, asteroid impacts, and the rise and fall of continents. The future of water on Earth is as fascinating as its past. As climate change alters precipitation patterns and sea levels rise, we're witnessing how delicate the balance of Earth's water systems truly is. Scientists are studying how ancient civilizations adapted to water scarcity and flooding, looking for lessons that could help us navigate the challenges ahead. Meanwhile, space agencies are developing technologies to extract water from lunar soil and Martian ice, recognizing that water will be the most precious resource for future space explorers. These efforts connect directly back to understanding how Earth got its water, because the same processes that delivered water here could help sustain human presence on other worlds. Perhaps most profound is how the study of Earth's water has changed our perspective on life in the universe. The discovery of extremophiles, organisms thriving in Earth's most inhospitable watery environments, has expanded our definition of habitable conditions. If life could emerge in Earth's early oceans, could it have also begun in the subsurface ocean of Europa or in the methane lakes of Titan? As we continue to explore these alien water worlds, we may find that Earth's relationship with water isn't unique, but rather one example of a universal pattern. The molecules that condensed on asteroids survived the violence of planetary formation and nurtured the first life on Earth, may have done the same on countless other worlds throughout the cosmos. Our search for water's origins has become a search for our place in the universe, and potentially for company in the cosmic ocean we all call home. The deeper we probe into Earth's watery origins, the more we realize how profoundly this single molecule has shaped our planet's destiny. Water didn't just passively accumulate on Earth. It actively transformed our world through a series of cascading effects. When enough water had collected to form persistent oceans, it began dissolving minerals from Earth's crust, creating the unique chemistry that would eventually support life. These primordial seas acted as giant reactors where simple molecules could concentrate and interact, while underwater volcanic vents provided both energy and mineral catalysts. The water cycle itself became Earth's first climate control system, regulating temperatures and weathering rocks to release nutrients. This dynamic interplay between water and rock set in motion the geological and chemical processes that made Earth habitable. Remarkably, Earth's water may have played a crucial role in developing the planet's magnetic field, our invisible shield against solar radiation. As water-bearing minerals were subducted deep into Earth's mantle, they altered the viscosity and flow patterns of molten rock in the outer core. These changes may have enhanced the geodynamo effect that generates our protective magnetic field. Without this shield, solar winds would have stripped away our atmosphere as they did on Mars, and life as we know it could never have evolved. Thus, the water delivered by asteroids didn't just fill our oceans, it may have helped create the very conditions necessary to keep that water from being lost to space. The story of Earth's water continues to evolve with cutting-edge research. Scientists are now using quantum mechanical calculations to model how water molecules behave under extreme pressures deep within Earth, revealing that our planet may hold several oceans worth of water locked in mantle minerals. Space missions to icy moons like Europa and Enceladus are showing us how water and rock interact in alien environments, providing new perspectives on Earth's own history. Meanwhile, astronomers are detecting water vapor in the atmospheres of exoplanets, allowing us to compare our water story with those unfolding around other stars. Each discovery reinforces the astonishing realization that the water in our bodies, our oceans, and our atmosphere is part of an immense cosmic cycle that predates our solar system. As we face global challenges like climate change and water scarcity, understanding Earth's water history becomes more than academic. It's essential for our survival. The same processes that brought water to Earth continue today, with tons of cosmic water still arriving annually via micrometeorites. While negligible compared to Earth's total water volume, this constant rain reminds us that our planet remains connected to the wider solar system. Looking ahead, humanity's expansion into space will depend on our ability to locate and utilize water resources on other worlds, making the lessons from Earth's watery past crucial for our future as a spacefaring civilization. The molecule that made our world unique in the solar system may ultimately become the key to leaving it. Ultimately, Earth's water represents one of the universe's most profound alchemies, the transformation of simple cosmic ingredients into the possibility of life. From interstellar clouds to planetary oceans, water has been both witness and participant in some of nature's grandest processes. As we continue to study its journey, we're not just uncovering our planet's history, we're learning how fragile and precious our watery world truly is in the vast expanse of space. The story of Earth's water, still being written after 4.5 billion years, remains humanity's most important story, because without it, none of our other stories would exist to be told. Space is a vast, silent expanse filled with celestial bodies moving in an intricate gravitational ballet. Among these are near-Earth objects, or NEOs, asteroids and comets whose orbits bring them close to our planet. Most are harmless, drifting by unnoticed, but a few demand our attention. One such object is asteroid 99942 Apophis, a rocky wanderer that will soon make one of the closest recorded flybys of Earth by an asteroid of its size. Discovered in 2004, Apophis quickly became infamous. Initial observations suggested a 2.7% chance of impact in 2029, a prediction that sent shockwaves through the astronomical community. Further analysis ruled out a collision for 2029, but the asteroid's upcoming passage remains historic. It will come closer than some human-made satellites, offering scientists an unprecedented opportunity to study a potentially hazardous asteroid up close. The asteroid was given its ominous name, Apophis, after the ancient Egyptian god of chaos and destruction, a fitting moniker for an object that had briefly threatened global catastrophe. The naming followed tradition, but it also cemented the asteroid's place in public consciousness as a symbol of existential cosmic threats. Even after the immediate danger was ruled out, Apophis remained a focus of intense study, both because of its close approach and because it represented a test case for how humanity might respond to future asteroid threats. What makes Apophis particularly interesting to scientists is not just its close approach, but its physical characteristics. Observations suggest it is an elongated, irregularly shaped body, possibly what astronomers call a rubble pile, a loose collection of rocks held together by gravity rather than a single solid mass. This structure has implications for how such asteroids behave when passing close to planets, as tidal forces could potentially disrupt them. The 2029 flyby will provide an unprecedented opportunity to study these effects up close. Scientists are particularly interested in whether Earth's gravity will cause measurable changes to Apophis's rotation or even trigger minor avalanches on its surface as the asteroid's weak gravity field is overwhelmed by our planet's pole. The scientific community is preparing for the 2029 encounter with an array of observational campaigns. Ground-based telescopes will track the asteroid's approach with increasing frequency as the date nears. Radar facilities, like the Goldstone Deep Space Communications Complex in California, will bounce signals off Apophis to create detailed maps of its surface. There have even been proposals for dedicated space missions to rendezvous with the asteroid during its flyby, though none have been funded yet. The data collected will not only satisfy scientific curiosity, but will also improve our ability to predict the orbits of other potentially hazardous asteroids in the future. Every close observation helps refine the models that keep us safe from cosmic impacts. Beyond the scientific value, the Apophis flyby carries significant cultural and psychological weight. It will be visible to the naked eye from certain parts of the world, a fast-moving point of light streaking across the night sky. For many, this will be a once-in-a-lifetime chance to witness a cosmic event of this magnitude. But it also serves as a visceral reminder that Earth exists in a cosmic shooting gallery, where chance encounters with space rocks have shaped the history of life on our planet. The dinosaurs famously met their end due to an asteroid impact. And while Apophis won't repeat that catastrophe, its close pass underscores that such events are not just ancient history, they are an ongoing part of our planetary existence. The Apophis story also highlights both the strengths and weaknesses of our current planetary defense systems. On one hand, the fact that we detected this asteroid years in advance and were able to precisely calculate its orbit demonstrates remarkable progress in asteroid tracking. On the other hand, the initial uncertainty about its trajectory shows how much more work remains to be done. There are likely many more Apophis-sized objects out there that we haven't yet discovered, and some of them could be on concerning trajectories. The lessons learned from tracking this asteroid are driving improvements in sky surveys and early warning systems that may one day prove crucial for protecting our planet. Looking beyond 2029, Apophis will continue to be an object of interest for astronomers. The close encounter with Earth will alter its orbit slightly, and precise measurements of these changes will provide valuable information about how gravitational interactions affect asteroid paths. Future close approaches, though none as dramatic as the 2029 event, will allow for continued study of this cosmic visitor. Some scientists have even speculated about the possibility of future missions to Apophis, either robotic or crewed, as its orbit makes it one of the more accessible near-Earth asteroids for exploration. The data gathered could inform not just planetary defense strategies, but also our understanding of asteroid composition and the early solar system. The tale of Apophis is ultimately one of both threat and opportunity. It represents the very real danger that near-Earth asteroids pose to our civilization, but also our growing ability to detect, track, and understand these threats. The 2029 flyby will be a milestone in asteroid science, offering researchers a front-row seat to observations that were unimaginable just a few decades ago. For the public, it will be a chance to look up and see a tangible piece of the cosmos passing remarkably close to our home planet. And for policymakers, it should serve as a reminder of the importance of continued investment in planetary defense, because while Apophis itself may not be a danger, the next asteroid we discover just might be. Deep in the velvet black of the constellation Leo, 120 light-years from the pale blue dot we call home, a revelation has emerged, one that will rewrite the story of life in the cosmos. The James Webb Space Telescope, humanity's most powerful eye in the heavens, has found it. A world where the air hums with the chemistry of life, where the temperature lingers at a perfect 120 degrees Fahrenheit, where vast oceans ripple beneath an alien sky. The data arrived like a whisper from the void, etched into the faint infrared light that had journeyed across the interstellar expanse for over a century. Dr. Niku Medusan, hunched over his monitor at Cambridge University, watched as the spectral lines unfolded, each one a fingerprint of molecules drifting through the atmosphere of a distant world. And then, there it was. A spike in the data, a signature that sent his pulse racing. Dimethyl sulfide, a molecule that, on Earth, is produced by only one thing: life. Not a trace, not a maybe, a signal so strong, so undeniable, that the odds of error were less than 3 in 1,000, 99.7% certainty. The number hung in the air like a thunderclap. The universe had spoken. We were no longer alone. The planet, designated K2-18b, is no mere exoplanet. It is a super-Earth, a world 8.6 times the mass of our own, wrapped in a hydrogen-rich atmosphere that acts like a cosmic blanket, cradling the planet in a perpetual, life-sustaining warmth. Unlike Earth, where the thin veil of nitrogen and oxygen leaves us vulnerable to the whims of space, K2-18b's thick hydrogen shroud locks in heat, redistributing it so efficiently that even the eternal night side, the hemisphere forever turned away from its dim red sun, remains bathed in liquid water. And then the implications hit like a comet strike. This world might be more hospitable than Earth itself. Red dwarf stars, like K2-18b's parent sun, are the silent sentinels of the galaxy, small, cool, and unfathomably long-lived. While our own sun will one day swell into a red giant and scorch Earth to cinders, K2-18b's star will burn for trillions of years, offering its planet an eternity of stable light. Life here would have time beyond human comprehension, to evolve, adapt, perhaps even transcend what we know as biology. But the true marvel lies in the chemistry. The James Webb Telescope didn't just find water vapor, methane, or carbon dioxide. It found dimethyl sulfide, a molecule that, as we know it, cannot exist without life. On Earth, it is exhaled by plankton, by bacteria, by the pulse of living oceans. And there, on a world 120 light-years away, it drifts in quantities so vast that they stain the very atmosphere. The implications are staggering. We have spent centuries searching for Earth's twin, a rocky world orbiting a sun-like star at just the right distance. But K2-18b is something else entirely, a planet that defies every assumption, a world where life thrives not despite its alien nature, but because of it. And this is only the beginning. Beneath the swirling hydrogen skies of K2-18b lies an enigma, an ocean unlike anything in our solar system. Not of pure water, but of water infused with hydrogen, a churning, pressurized abyss where the rules of chemistry twist into something alien, and yet something alive. This is no ordinary sea. Earth's oceans are fragile things, bound by narrow temperatures and pressures, vulnerable to freezing or boiling away into the void. But K2-18b's ocean is different. Here, dissolved hydrogen acts as a universal solvent, stabilizing the water across a mind-bending range of conditions, from near freezing to scalding beyond 300 degrees Fahrenheit. Life here would not cling to survival at the edges of possibility. It would flourish. The pressure is crushing, hundreds of times greater than Earth's deepest trenches, yet the hydrogen-laced waters resist the physics that would turn them to ice or steam elsewhere. Instead, they remain liquid, a vast global reservoir stretching hundreds of miles deep. Imagine it. An entire planet's worth of water, so much that Earth's oceans would be mere puddles in comparison. And within those depths, on Earth, hydrogen is a trace gas, a flicker in the atmosphere. But on K2-18b, it is the foundation of life itself. Microbes here, if they can even be called that, might not rely on oxygen, but on hydrogen as their energy source, metabolizing it in ways that would seem impossible in our own biosphere. They would not exhale carbon dioxide, but dimethyl sulfide, the very molecule that announced their existence to us across the interstellar gulf. High in K2-18b's atmosphere, where pressures warp carbon into crystalline structures, microscopic diamonds form and fall like glittering snow. On Earth, such a phenomenon would be a wonder. Here, it is weather. The planet's methane swirls in vast storms, reacting with hydrogen to create complex organic chains, the building blocks of life, cycling endlessly through air and sea. But the most haunting question remains: what kind of life could thrive here? If Earth's extremophiles, those microbes clinging to volcanic vents or buried in Antarctic ice, are any indication, life is stubborn. But K2-18b is not merely extreme, it is optimized. Its thick atmosphere shields it from deadly stellar flares. Its global ocean ensures no desert wastelands, no frozen poles, just an unbroken temperate expanse. Evolution here would have no bottlenecks, no mass extinctions from ice ages or overheating. Life could grow uninterrupted for billions of years. And that raises a terrifying, exhilarating possibility. What if we're not looking at microbes? What if, beneath those hydrogen waves, something more is waiting? The final revelation of K2-18b comes not from what we can see, but from what we must now accept. The data leaves no room for doubt. We stand at the threshold of a new cosmic paradigm. This distant world, with its hydrogen-rich atmosphere and global ocean, has rewritten the rules of where life can exist. No longer must we search only for pale reflections of Earth. The universe has shown us something far more profound: that life adapts, thrives, and perhaps even prefers environments we once thought impossible. The implications ripple outward like shock waves. If a super-Earth orbiting a red dwarf can harbor life, then the number of habitable worlds in our galaxy may be tenfold what we imagined. Each faint red sun in our night sky, once dismissed as an unlikely host for planets, now glows with new promise. The dimethyl sulfide signature in K2-18b's atmosphere represents more than just a scientific discovery. It is a mirror held up to our place in the cosmos. We are not special. We are not alone. We are simply one expression of a universe teeming with possibilities. The James Webb Space Telescope has given us our first real answer to humanity's oldest question, and in doing so, has birthed countless new ones. What forms might life take in that hydrogen ocean? What civilizations might have risen and fallen over the eons of K2-18b's existence? The planet's stability means life there could be older, more advanced, or utterly alien compared to anything on Earth. As we continue to study this distant world, we must prepare ourselves for an even more profound truth. That not be unique. It may simply be the first of many such worlds we discover, each rewriting our understanding of biology, chemistry, and the very nature of existence. The discovery marks not an end, but a beginning, the opening chapter in humanity's true understanding of our place among the stars. The universe has spoken. Life is everywhere, and we are just beginning to listen. For centuries, humanity gazed at the stars and made a fundamental assumption. We believed that our little corner of the cosmos, our solar system, was the standard model. We had a neat and orderly arrangement, a single star at the center, a set of inner rocky planets, a belt of asteroids, and then the gas giants orbiting further out. This configuration seemed so logical and elegant that we developed a beautiful theory, the nebular hypothesis, to explain its formation. It was a perfect story that neatly described everything we saw right here at home. This was the picture of the universe we held in our minds before we began to discover worlds beyond our sun. The moment we started finding exoplanets, that entire picture shattered. One of the very first types of planets we discovered defied all logic and expectation: the hot Jupiters. Imagine a planet. Now imagine a planet with the mass of Jupiter, a colossal giant of gas. Now imagine that planet not orbiting far out in the cold depths of space, but parked impossibly close to its star, 20 times closer than Mercury is to our Sun. When these objects were first detected, the scientific community was deeply skeptical. It made no sense within our existing models. How could a gas giant form so close to the searing heat of a star? The initial reaction was outright disbelief. The proof arrived when one of these bizarre objects was observed transiting its star, passing directly in front of it and causing a detectable dip in starlight. This confirmation forced a profound and humbling revolution in our thinking. We had to throw out the textbook and start again. The current leading theory is a violent and chaotic one. These hot Jupiters likely form in the outer reaches of their systems, much like our own Jupiter. But through gravitational interactions, a cosmic dance of instability, they are kicked inward. They get flung into wildly eccentric orbits that, over immense periods of time, circularize incredibly close to their parent star. While they are unusual, occurring in only about 1% of systems, their existence was our first major clue that our solar system is not the norm. The surprises did not stop with hot Jupiters. We soon found another class of world entirely absent from our own planetary family, mini Neptunes. These are planets that occupy the size gap between Earth and Neptune, typically about 2 to 4 times the radius of our homeworld. Our solar system has nothing like this. Is a mini Neptune a massive rocky planet, a so-called super-Earth? Or is it a small gas-enveloped world, a true miniature version of Neptune, perhaps with a vast global ocean? The astonishing fact is that this type of planet, which we have no example of here, appears to be the most common type of planet in the entire galaxy. Our solar system is missing the most ubiquitous planet in the universe. This strangeness extends to the planets we do have. Take Jupiter itself. This massive planet has played a crucial role in the history of our system, potentially shepherding material and influencing the development of the inner planets. Yet data from missions like Kepler, which has discovered thousands of exoplanets, suggests that only about 10% of Sun-like stars host a Jupiter-sized planet. Our system doesn't just have one, it has two, with Saturn being a gas giant in its own right. Furthermore, simply having 8 stable planets is itself a relative rarity. Many systems we observe have fewer planets, often packed much closer together than ours are. Even our Sun's solitary nature is unusual. We take it for granted that a star shines alone, but the cosmos prefers company. Approximately half of all star systems are binary, consisting of 2 stars orbiting a common center of gravity. Some are even trinary systems, with 3 stars locked in a complex gravitational dance. The nearest star system to us, Alpha Centauri, is a perfect example. It consists of Alpha Centauri A and B, a tight binary pair, and then Proxima Centauri, a red dwarf that orbits them both at a much greater distance. The dynamics of planets in such multi-star systems must be incredibly complex, with orbits that could be highly eccentric or unstable compared to our relatively placid and circular paths. This raises a profound question about our place in the cosmos. Is our solar system special? The evidence is mounting that it might be an outlier in several key ways. We orbit a stable single star, a G-type main sequence star, which is itself not the most common model. The most populous stellar class in the Milky Way is the red dwarf, small, cool stars that make up about 75% of the stellar population. Our Sun is in a minority. We have a full suite of planets, including a giant planet in Jupiter that seems to be relatively uncommon. And we are missing a mini Neptune, the galaxy's most popular model of planet. The diversity of exoplanets tells a story of chaos and dynamism. It suggests that the formation of planetary systems is a violent, unpredictable process. The serene order of our solar system might be the exception, not the rule. This has direct implications for the search for life. Our system provided a stable billion-year cradle for life to arise and evolve on Earth. If most systems are more chaotic, with planets being ejected, migrating inward, or experiencing intense stellar radiation from multiple suns, the number of stable, habitable environments could be far lower than we once optimistically hoped. Our understanding of how systems form begins in vast clouds of gas and dust, known as molecular clouds. These are the nurseries of stars and planets. Within these clouds, slight density fluctuations begin to collapse under their own gravity. As a region collapses, it spins faster, flattening into a protoplanetary disk. At the center, the pressure and heat ignite nuclear fusion, and a star is born. In the surrounding disk, dust grains begin to stick together, forming pebbles, then rocks, then planetesimals, and eventually planets. This is the nebular theory, and it remains our best framework. However, the devil is in the details. The precise mechanisms of how you go from microscopic dust grains to massive planets are still not fully understood. This is a frontier of modern astrophysics, involving incredibly complex supercomputer simulations that model the collisions, accretions, and gravitational interactions of trillions of particles. It is a chaotic and nonlinear process, and slight differences in initial conditions, the amount of material, the stellar mass, the presence of a nearby supernova, can lead to wildly different outcomes. An orderly system like ours, a system with hot Jupiters, or a system dominated by mini-Neptunes. When we look up at the night sky, we are not looking at a universe filled with copies of our solar system. We are looking at a cosmic zoo of planetary possibilities, a menagerie of strange and wonderful worlds that defy our earthly imagination. We built our theories from a single data point, our home. Now, with thousands of new data points, we see a universe that is far more creative, far more violent, and far more diverse than we ever dreamed. Our solar system, with its quiet stability and its life-bearing world, begins to look less like a common blueprint and more like a rare and precious jewel. This growing catalog of cosmic oddities forces us to confront a deeply profound and humbling possibility. The Earth may not just be unusual, but virtually unique. The concept of rare Earth suggests that the confluence of conditions necessary for a stable, life-bearing planet like ours is so exceptionally specific that it might be an extraordinary fluke in an otherwise barren and chaotic universe. We are not just looking for another planet with liquid water. We are looking for a planet that has maintained a delicate equilibrium for billions of years. Consider the chain of events that led to us, a stable, solitary star of the right size and longevity, the presence of a Jupiter-like giant in just the right orbit to act as a gravitational shield, deflecting comets and asteroids that might otherwise cause constant extinction-level events. Our large moon, likely formed from a cataclysmic impact in the solar system's youth, which stabilizes Earth's axial tilt, preventing wild climatic shifts that would render complex life impossible. The precise plate tectonics that recycle nutrients and regulate our planet's temperature over eons. Each of these factors is, by itself, not necessarily ultra-rare. But the probability of all of them and dozens more occurring simultaneously in one system and persisting in a stable harmony for over 4 billion years is astronomically low. It transforms the emergence of intelligent life from a near inevitability given enough time and space into a precarious 1 in a trillion long shot. The universe is vast, but its sheer size does not guarantee that this specific, intricate recipe has been repeated elsewhere. This leads to the unsettling conclusion that we might truly be alone. The Fermi paradox, the question of where all the aliens are, may have a very simple and lonely answer: they do not exist. The great silence we hear when we listen to the cosmos is not because civilizations are hiding or have transcended. It is because there is no one else out there to call. We gaze at the countless stars, not as potential homes for other societies, but as beautiful, empty, and sterile nuclear furnaces. In this view, our planet is not just a pale blue dot, it is a sanctuary, a singular, fragile oasis of consciousness in a breathtakingly vast and silent desert of space. The absence of alien megastructures, signals, or visitors is not a puzzle to be solved, but the expected outcome of a universe where the ingredients for life are so impossibly scarce. This realization imbues our existence with a profound responsibility. If we are the universe's only way to know itself, then our mission becomes infinitely more critical. The preservation of our biosphere and our species is not just a local concern, it is a cosmic imperative. We are not just inhabitants of Earth, we may be the only sentient guardians of meaning in a silent, unconscious cosmos, and the only ones who can appreciate its terrifying and beautiful emptiness. The changing seasons we experience annually represent just one layer in a complex hierarchy of climate cycles that operate across vastly different timescales. While most people understand that Earth's axial tilt creates our regular seasonal patterns, few appreciate how this tilt interacts with other planetary motions to produce much longer climate cycles that have shaped human evolution and geological history. These grand climatic rhythms, known as Milankovitch cycles, after the Serbian mathematician Milutin Milanković, who first systematically described them in the 1920s, emerge from subtle variations in Earth's orbital characteristics over thousands of years. They explain why our planet periodically plunges into ice ages, and why the timing of seasons slowly shifts across the calendar over millennia. Understanding these cycles provides crucial context for both Earth's climatic past and the potential trajectories of our climate future. At the most fundamental level, Earth's climate variations stem from how solar energy gets distributed across the planet's surface. The total amount of energy Earth receives from the Sun remains remarkably constant. What changes is where and when that energy arrives. Three primary orbital characteristics govern this distribution: eccentricity, the shape of Earth's orbit around the Sun; obliquity, the tilt of Earth's axis relative to its orbital plane; and precession, the slow wobble of Earth's rotational axis. Each of these parameters vary cyclically over different timescales, creating complex interference patterns in Earth's climate system. The 100,000-year eccentricity cycle, the 41,000-year obliquity cycle, and the 26,000-year precession cycle interact to produce the major climatic variations we see in the geological record. The eccentricity cycle, operating on a 100,000-year timescale, describes how Earth's orbit oscillates between more circular and more elliptical shapes. Currently, Earth's orbit is nearly circular, with only about 3% difference between its closest, perihelion, and farthest, aphelion, points from the Sun. However, at maximum eccentricity, this difference can reach nearly 30%, significantly altering the solar radiation Earth receives at different points in its orbit. What makes this cycle particularly important for climate is how it interacts with the precession cycle, the timing of when these orbital extremes occur relative to Earth's seasons. Currently, perihelion occurs in early January during Northern Hemisphere winter, meaning our winters are slightly milder than they would be otherwise. But this configuration slowly changes over thousands of years due to precession. Obliquity, or axial tilt, represents perhaps the most intuitive of the Milankovitch cycles. Earth's current 23.4-degree tilt relative to its orbital plane creates our familiar seasons. However, this tilt varies between about 22.1 and 24.5 degrees over a 41,000-year cycle. When the tilt is greater, seasonal contrasts become more extreme. Summers become hotter and winters colder in both hemispheres. Reduced tilt leads to more muted seasonal differences. Currently, Earth's tilt is decreasing from its maximum, meaning we're in a phase of gradually less extreme seasonal variations. This might seem like it would lead to warmer conditions overall, but paradoxically, the geological record shows that ice ages tend to begin when tilt is decreasing, because milder summers allow winter snow accumulation to persist year-round in high latitudes, beginning the process of ice sheet growth. The precession cycle, sometimes called the wobble of Earth's axis, completes the Milankovitch triad. Over about 26,000 years, Earth's rotational axis traces a circle in space, much like a spinning top winding down. This means that which celestial pole star we have, currently Polaris, changes over time. And more importantly for climate, it changes which hemisphere experiences summer when Earth is closest to the Sun. Today, the southern hemisphere has summer at perihelion, receiving about 7% more solar radiation during its summer than the northern hemisphere does. In 13,000 years, this situation will reverse, with the northern hemisphere gaining the advantage of summer at perihelion. This cycle is particularly important because it determines whether the amplification of solar radiation from eccentricity affects summer or winter in each hemisphere. The interaction of these three cycles creates the complex pattern of climate variation seen in ice core and sediment records. For instance, the 100,000-year cycle of ice ages that has dominated the past million years appears to result from a particular combination of eccentricity, obliquity, and precession that allows ice sheets to persist and grow in the northern hemisphere. The relatively weak 100,000-year eccentricity cycle appears amplified in the climate record because of feedback mechanisms in the Earth's system, particularly the reflectivity, albedo, of expanding ice sheets and the atmospheric concentration of greenhouse gases that vary in sync with these orbital changes.
Understanding these cycles requires examining how they affect solar radiation distribution across Earth's surface. Astronomical calculations show that summer insolation, incoming solar radiation, at 65 degrees north latitude appears particularly important for ice sheet growth and retreat. When summer insolation at these high northern latitudes falls below a certain threshold, winter snow accumulation can survive through the summer, beginning the process of ice sheet growth. The current configuration of Milankovitch cycles suggests we're in a relatively stable interglacial period that would typically last about 10,000 to 15,000 more years before the next glacial period begins. However, the unprecedented rise in greenhouse gas concentrations from human activities has introduced a wild card into this natural cycle. The geological record provides compelling evidence for the influence of Milankovitch cycles. Deep-sea sediment cores show regular variations in oxygen isotope ratios that reflect changes in global ice volume over the past several million years. These records reveal that the dominant periodicity of ice ages changed about 1 million years ago from a 41,000-year cycle, matching obliquity, to a 100,000-year cycle, matching eccentricity, in what scientists call the mid-Pleistocene transition. The reasons for this shift remain debated, but likely involve long-term cooling trends that made ice sheets more sensitive to particular orbital configurations. Modern climate science continues to refine our understanding of how Milankovitch cycles interact with other climate forcings. While these orbital variations provide the pacemaker for ice age cycles, they work in concert with greenhouse gas concentrations, ocean circulation patterns, and tectonic changes to produce the actual climate variations we observe. The relatively weak changes in solar radiation from orbital variations get amplified by feedbacks in the climate system, particularly through changes in ice cover, vegetation patterns, and atmospheric composition. This explains why the 100,000-year eccentricity cycle, which produces only minor changes in total annual solar radiation, can nonetheless drive massive glacial interglacial cycles. The implications of Milankovitch theory extend beyond academic interest. Understanding these natural climate cycles helps contextualize current anthropogenic climate change against Earth's longer-term variability. It also provides insights into potential climate futures, both the natural cooling trend we might expect over the coming millennia in the absence of human influence, and how anthropogenic warming might interact with these natural cycles. As we continue to alter Earth's atmosphere and surface, the lessons from Milankovitch cycles remind us that small, sustained changes to Earth's energy balance can produce dramatic climate transformations over time. The apparent contradiction between the modest variations in solar radiation caused by Milankovitch cycles and the dramatic climate shifts they produce represents one of the most fascinating puzzles in paleoclimatology. While Earth's orbital parameters change only slightly over millennia, these subtle alterations somehow trigger continental-scale glaciation and deglaciation events that reshape entire ecosystems. This amplification occurs through a series of powerful feedback mechanisms that transform small astronomical nudges into global climate revolutions. The transition from interglacial warmth to ice age conditions typically begins when orbital configurations lead to slightly cooler summers in critical northern latitudes, just enough to allow winter snow accumulation to persist through the warmer months. What begins as a minor change in seasonal snow cover escalates into a planetary-scale transformation through three primary amplifiers: the ice albedo feedback, the greenhouse gas feedback, and ocean circulation changes. The ice albedo feedback provides the most straightforward amplification mechanism. As ice and snow accumulate, they increase Earth's albedo, causing more incoming solar radiation to bounce back into space rather than being absorbed as heat. This cooling allows ice sheets to expand further, increasing albedo even more in a self-reinforcing cycle. Climate models suggest that this feedback alone can triple the initial cooling from orbital changes. During the last glacial maximum, about 20,000 years ago, ice sheets covering much of North America and Europe increased Earth's albedo by about 30% compared to today, reflecting enough sunlight to lower global temperatures by an additional 4 to 5 degrees Celsius beyond the direct effects of reduced summer insolation. The growth of these ice sheets wasn't gradual. Geological evidence shows they expanded in rapid pulses when certain climate thresholds were crossed, demonstrating the non-linear nature of ice albedo feedbacks. Equally important is the greenhouse gas feedback, which acts in concert with ice albedo effects. Ice core records from Antarctica reveal an astonishingly tight correlation between atmospheric CO2 concentrations and global temperatures over the past 800,000 years. During glacial periods, CO2 levels dropped to about 180 parts per million, compared to pre-industrial levels of 280 ppm, while during interglacials they rose to 280 to 300 ppm. This variation accounts for roughly half of the temperature difference between glacial and interglacial conditions. The mechanisms linking orbital forcing to CO2 changes involve complex interactions between the atmosphere, oceans, and biosphere. Cooling oceans absorb more CO2, while expanded ice sheets reduce the area available for plant growth, decreasing carbon storage in terrestrial ecosystems. Changes in ocean circulation patterns may also affect the rate at which deep ocean carbon reservoirs exchange with the atmosphere. These processes create another powerful positive feedback loop, where initial cooling reduces atmospheric greenhouse gases, which causes further cooling.
Ocean circulation patterns provide the third major amplifier of Milankovitch forcing. The Atlantic Meridional Overturning Circulation, AMOC, which includes the Gulf Stream, plays a particularly crucial role in climate transitions. As ice sheets grow and freshwater input to the North Atlantic increases from melting icebergs, the AMOC can weaken or even collapse, dramatically reducing heat transport to northern latitudes. Paleoclimate evidence shows that such disruptions occurred repeatedly during the last glacial period, causing abrupt regional cooling events of up to 10 degrees Celsius in just decades. These ocean circulation changes help explain why Milankovitch forcing affects climate differently in various regions. While orbital changes distribute solar energy relatively evenly across the globe, their effects get channeled through ocean and atmospheric circulation patterns that create strongly regionalized climate responses. The tropics, for instance, experience relatively small temperature changes during glacial cycles, but significant variations in precipitation patterns. The timing of ice age cycles relative to Milankovitch forcing reveals another layer of complexity. Detailed analysis of ice core records shows that changes in greenhouse gas concentrations and global temperature often lag behind the orbital changes that initiated them by several thousand years. This lag occurs because the growth and decay of massive ice sheets represents a slow physical process. It takes time for accumulated snowfall to compress into ice and flow outward into continental-scale glaciers. Similarly, the ocean's thermal inertia means that surface temperatures respond gradually to changes in solar forcing. However, once certain thresholds are crossed, climate transitions can occur remarkably quickly. The end of the last ice age featured several instances where global temperatures rose 5 to 10 degrees Celsius in just a few decades, likely triggered by sudden reorganizations of ocean circulation or rapid ice sheet collapse.
The mid-Pleistocene transition, which occurred about 1 million years ago, marks a crucial change in how Milankovitch cycles affected Earth's climate. Before the MPT, ice ages followed a 41,000-year cycle, matching the obliquity period. Afterward, they shifted to a 100,000-year cycle, matching eccentricity. This transition remains incompletely understood, but likely involved long-term cooling that made ice sheets more sensitive to particular orbital configurations. One theory suggests that gradual atmospheric CO2 decline made the climate system more responsive to eccentricity variations. Another proposes that glacial erosion changed the bedrock topography beneath northern hemisphere ice sheets, making them more stable and long-lasting once they formed.
Regardless of the exact mechanism, the MPT demonstrates that the relationship between orbital forcing and climate response evolves over geological timescales. Modern climate science continues to refine our understanding of these feedback mechanisms through increasingly sophisticated computer models. These models can simulate how small changes in solar forcing get amplified into full glacial-interglacial cycles, helping identify which feedbacks matter most under different conditions. Recent work suggests that atmospheric dust levels may represent another important amplifier. As ice sheets expand, they create drier conditions that increase dust deposition on remaining ice and snow, reducing their reflectivity and accelerating melting. This negative feedback may help trigger the relatively rapid deglaciations seen in the paleoclimate record. Other studies focus on how vegetation changes interact with ice sheet growth, as expanding tundra replaces forests at high latitudes, further increasing surface reflectivity. The implications of these feedback mechanisms extend beyond academic interest. They demonstrate that Earth's climate system contains multiple tipping points where small, gradual forcing can produce large, rapid changes. This understanding informs contemporary climate change research by showing how anthropogenic warming might trigger similar feedbacks in reverse. Melting Arctic sea ice reduces albedo, warming oceans release CO2, and thawing permafrost emits methane. While the current human-driven warming occurs much faster than natural orbital changes, the paleoclimate record provides crucial evidence about how Earth's climate system responds to various forcings over different timescales. Looking ahead, Milankovitch's theory predicts that, in the absence of human influence, Earth would gradually cool over the next 20,000 years toward another glacial period. The current interglacial period, the Holocene, has already lasted about 11,700 years, comparable in length to previous interglacials. However, the unprecedented rise in atmospheric CO2 from human activities has almost certainly disrupted this natural cycle. Climate models suggest that unless CO2 concentrations fall dramatically, the next ice age may be postponed by 100,000 years or more. This human intervention in Earth's astronomical climate rhythms represents an unplanned global experiment whose full consequences remain uncertain. The study of past Milankovitch cycles reminds us that Earth's climate has always changed, but also that human activities now rival astronomical forces as drivers of that change.
The delicate interplay between Earth's orbital cycles and climate systems now faces unprecedented disruption from human activity, creating a new geological epoch where anthropogenic forces compete with celestial mechanics. For the past 2.6 million years, the Pleistocene's glacial-interglacial rhythm has pulsed to the beat of Milankovitch cycles. But our current Holocene interglacial period has developed a new tempo shaped by industrial civilization. This collision between astronomical and human-driven climate forcing presents a profound scientific and societal challenge: how to reconcile the natural rhythms that have governed Earth's climate for millions of years with the rapid changes induced by greenhouse gas emissions. The paleoclimate record suggests we should currently be in a period of very gradual cooling, with summer insolation at 65 degrees north having peaked about 11,000 years ago and slowly declining toward conditions that might, in several thousand years, favor the growth of continental ice sheets. Instead, human activities have reversed this trend so dramatically that current CO2 levels at 420 parts per million exceed anything in the past 3 million years, effectively short-circuiting the natural progression toward the next ice age. This human intervention in Earth's astronomical climate cycles raises fundamental questions about how natural and anthropogenic forcings will interact in coming centuries. Climate models incorporating both Milankovitch cycles and projected greenhouse gas scenarios suggest that the next glacial inception, which might normally occur in about 50,000 years under natural conditions, could be delayed by 100,000 or more, depending on emission trajectories. The duration of this postponement depends critically on how long elevated CO2 persists in the atmosphere, a factor complicated by various carbon cycle feedbacks that are still not fully understood. Deep ocean sediment studies show that during past interglacials with similar orbital configurations to today, particularly marine isotope stage 11 around 400,000 years ago, interglacial conditions persisted for 20,000 to 30,000 years, nearly twice the length of typical interglacials. This geological precedent suggests that even without human influence, the current interglacial might have been exceptionally long, but anthropogenic warming has taken this possibility to extremes beyond anything in the Pleistocene record.
The concept of planetary boundaries provides a useful framework for understanding how human activities interact with Milankovitch cycles. Researchers have identified 9 critical Earth system processes that maintain the stable Holocene conditions which enabled human civilization to flourish, with climate change and biosphere integrity considered core boundaries. Milankovitch forcing traditionally operated well within these boundaries, causing climate variations that, while significant, remained within limits that allowed ecosystems to adapt through migration and evolution. Human-driven climate change, by contrast, is pushing the system toward thresholds that may trigger irreversible changes on timescales irrelevant to traditional astronomical cycles. The rate of current CO2 increase is about 100 times faster than the most rapid natural rises seen in ice core records, leaving insufficient time for many species and ecosystems to adapt. This creates a peculiar situation where we are simultaneously preventing the next ice age while potentially creating climate disruptions more severe than typical glacial-interglacial transitions. The relationship between Milankovitch cycles and contemporary climate change also informs debates about climate sensitivity. How much global temperature changes in response to radiative forcing? Paleoclimate evidence from past interglacials suggests that Earth's climate system is highly sensitive to relatively small changes in energy balance when certain thresholds are crossed. During the transition out of the last ice age, for example, a mere 0.3% increase in total solar radiation reaching Earth triggered a 5 degrees Celsius global warming through powerful feedback mechanisms. This historical precedent raises concerns that human-caused forcing may similarly engage feedbacks that amplify warming beyond what basic greenhouse gas concentrations would predict. Current observations already show these amplifiers at work. Declining Arctic sea ice reduces albedo, melting permafrost releases methane, and warmer oceans hold less CO2. All reinforcing the initial warming trend in ways reminiscent of, but much faster than, natural interglacial warming periods.
Milankovitch theory also provides insights into regional climate patterns that may emerge under anthropogenic warming. Paleoclimate data show that orbital forcing affects precipitation patterns differently in various parts of the world, with monsoon systems being particularly sensitive to insolation changes. During periods when Northern Hemisphere summer insolation was stronger than today, as it was 8,000 to 10,000 years ago, the African monsoon was more intense, creating a green Sahara with extensive lakes and savanna vegetation where there is now desert. These past conditions, caused by orbital configurations that enhanced seasonal temperature contrasts, provide potential analogs for how regional rainfall patterns might shift under human-caused climate change. However, the rapid pace of current warming and the different spatial pattern of radiative forcing, greenhouse gases distribute heat differently than orbital changes, mean that exact paleoclimate analogs may not exist for the coming century. The long-term perspective provided by Milankovitch cycles also helps contextualize debates about climate stabilization targets. The Paris Agreement's goal of limiting warming to 1.5 to 2 degrees Celsius above pre-industrial levels represents a deliberate attempt to keep Earth's climate within the range of variability experienced during the Holocene. However, even this safe range includes temperatures warmer than any point in the past 120,000 years, and sustained CO2 levels above 350 ppm may already commit Earth to changes outside the envelope of recent interglacials. Climate models that incorporate both Milankovitch forcing and anthropogenic emissions suggest that unless CO2 is actively removed from the atmosphere, the current interglacial climate state could persist for tens of thousands of years longer than natural cycles would dictate, potentially skipping the next 1 to 2 glacial periods entirely. This would represent one of the most lasting and conspicuous human impacts on the Earth system, visible in geological strata millions of years hence.
The study of Milankovitch cycles in the Anthropocene also raises profound questions about humanity's relationship with deep time. For the first time in Earth's history, a single species has developed the capacity to alter planetary-scale climate processes that were previously governed solely by astronomical and geological forces. This power brings with it responsibility to understand the climate system we are disrupting, to anticipate the consequences of our actions across multiple timescales, and ultimately to decide what kind of climate future we want to create. The paleoclimate record shows that Earth's climate can exist in multiple stable states, glacial and interglacial being just two, and that transitions between these states often occur rapidly once certain thresholds are crossed. As we push the climate system beyond the range of natural variability documented in ice cores and ocean sediments, we risk triggering changes that could persist for millennia, long after any conceivable fossil fuel era has ended. Looking ahead, the integration of Milankovitch theory with climate change research will likely focus on several key areas. Improved understanding of carbon cycle feedbacks will help predict how long anthropogenic CO2 will remain elevated, and how this might affect future orbital-scale climate evolution. Better reconstructions of past interglacials will provide crucial data points for how Earth's climate behaves under slightly warmer conditions than the Holocene. And refined climate models will continue to explore how orbital forcing and greenhouse gas changes interact across different timescales. Perhaps most importantly, the long-term perspective provided by Milankovitch studies reminds us that climate change doesn't end in 2100. The decisions we make today about energy systems and emissions will shape Earth's climate trajectory
for tens to hundreds of thousands of years, potentially overriding the natural astronomical rhythms that have governed ice age cycles for millions of years. In this context, the current geological epoch represents not just another turn of the celestial climate cycle, but a fundamental transformation in how Earth's climate functions. A transformation where human choices now rival orbital mechanics as determinants of planetary climate destiny.
The slow, rhythmic dance of Earth's axial tilt, oscillating between 22.1 degrees and 24.5 degrees over 41,000 years, has long dictated the pulse of our planet's climate. Today, we find ourselves in an epoch of transition, not just astronomically, but anthropogenically. The current tilt of 23.44 degrees, now gradually decreasing since its peak in 8700 BCE, would naturally guide Earth toward cooler summers and the slow accumulation of ice sheets over millennia. Yet human activity has disrupted this ancient rhythm, injecting greenhouse gases into the atmosphere at a rate that dwarfs the incremental changes driven by orbital cycles. The Holocene's relatively stable climate, which nurtured the rise of civilization, is giving way to the Anthropocene, an era where human influence rivals the gravitational forces that once solely governed Earth's climate destiny. The interplay between Milankovitch cycles and anthropogenic warming presents a paradox. On one hand, the current phase of decreasing obliquity might have otherwise set the stage for a gradual return to glacial conditions, with milder summers allowing snow to persist at high latitudes. On the other, the sheer magnitude of human-caused warming has overridden these subtle astronomical cues, potentially delaying the next ice age by tens of thousands of years. This divergence underscores a profound truth. While Earth's orbital mechanics still operate with the same celestial precision, their climatic influence is now mediated and in some cases muted by human activity.
Yet, the legacy of Milankovitch cycles endures. They remind us that climate change is not a novel phenomenon, but a fundamental feature of Earth's history. The difference now lies in the speed and scale of change, as well as our unique capacity to comprehend and alter these processes. As we peer into the future, the lessons of these cycles offer both caution and hope. Caution, because they reveal how small perturbations can cascade into planetary-scale transformations through feedback loops like ice albedo and greenhouse gas amplification. Hope, because they demonstrate Earth's resilience and the possibility of finding equilibrium, even after dramatic shifts. The angle of Earth's axial tilt, now midway through its 41,000-year journey, will continue its silent sway, indifferent to human affairs. But for the first time in 4.5 billion years, a species has emerged that can read these cosmic rhythms, foresee their consequences, and choose whether to harmonize with them or rewrite their score. The challenge ahead is not just to mitigate climate change, but to align our actions with the deeper temporal wisdom encoded in Earth's orbital cycles. In doing so, we might yet forge a future where humanity's brief but fiery epoch leaves behind not just disruption, but a renewed appreciation for the delicate balance that sustains life on this pale blue dot, suspended in the grand celestial symphony.